All right. Another week, another office hours. Seems like it's live. Maybe. It's being weird on my phone. Oh, there it goes. And we have audio. Sweet. All right. All right. Well, welcome to this week's office hours on race conditions. I guess let's jump into it. Are there any questions to start us off for the office hours? Guess let's see how many people have solved challenges so far. Some number of solves. Haven't started. Yeah, that is definitely the issue of my office hours being the day after the launch. It's much less likely that people have had a chance to start. Guess just to be sure, I will post in the announcements that have office hours. Sweet. All right, so I see in the chat there is a question about level 3 and level 4. Okay. Let's start by taking a look at level 3. And I think I'm going to keep using SSH. Yeah, we'll go with SSH. Okay, so level 3. If we go to run the challenge, we will see immediately assertion failed. Then that makes sense because the previous levels we've already seen that these levels are looking for an argv1. And we can see in the initial description, now that I have the camera in the top right, what do I do when there's text at the top of the screen? Sweet. Okay. It's looking for a file path as argv1. It's telling us that the file opened will be read in. Let's see here. File's path does not include flag. Verify that the file is not a symlink. Verify that the file is not larger than 256 bytes. Okay, that sounds unique. What do we want to start as a demo of this? How large is Etsy password? That is definitely too large. Whatever, we could just create a random file. Actually, to be safe, let's do it in our home directory. Demo, okay. Let's create a file called world. And that will contain the string hello. And if we run this challenge with this file path, okay, it tells us it is going to call lstat, does not follow symlinks. Okay, so basically lstat is going to get a bunch of information about the file path that we've given the program, and it's going to be able to, for instance, determine the size of the file using that. And there's some difference between using lstat versus using stat, which is that lstat will not follow simlinks. So it will, for instance, since this syscall is all about finding metadata about a file, if it's a symlink, you might want to be able to determine, hey, this file is a symlink. And lstat will allow you to do that because it won't actually follow the symlink. So this lstat syscall is going to allow the program to do, at a minimum, this constraint check, that, hey, this file is not a symlink. And if we press enter to continue, presumably that passed. And then there was another. Okay, and then in this case, it tells us value of win variable 0. Okay, so interesting. So probably just guessing, we want to make the value of win variable not be 0 if we just think back to previous modules. And that would probably also follow reasonably with the fact that, hey, this file needs to only be 256 bytes or less. Presumably, since this is all about race conditions, if we can get this to be more than 256 bytes, that's probably how we're going to overflow this win variable, especially since it's telling us the file is going to be opened and read in. Okay, so let's confirm that though. So if I do cp hacker at dojo.pwn.college and we grab the challenge file, and we open this up in IDA. Okay, and let's take a look at what this is actually doing, just to verify it, you know. Probably our assumptions are correct, but it'll probably help to confirm this. Okay, so we can see that decompiling this, it's doing that lstat. Oops, did not want to double click that. It's doing the lstat to get information about the file. And it's doing this check on this st mode thing, and it's anding that with 0xf00 and making sure that that equals this value. So not entirely sure why you would do it in this way. Oh, because you want to make sure some other bits are 0. Yeah, okay. So it's doing this check, and it's going to tell us, hey, the file is a symlink if this is true. So presumably that's all set up correctly. But in the worst case, this would be a thing to investigate. You know, make sure all these bits are correct for what we want it to do. And then here's where it's checking to see if the size is greater than 256, in which case it would tell us, hey, this file is too large. So for instance, if we do the challenge and pass it etc password, we will see that error message, hey, the file is too large because etc password is, we saw like 1200, 1300 bytes, just too large. Okay. And then it reads hex 1000 bytes in, but it, you know, this should be safe because, you know, it already checked that it's not greater than 256, so who cares, you know, just read in a larger number, it shouldn't be an issue. And then it tells us the value of this win variable, so win variable, and if this is non-zero, it will win for us. And where is this win variable located? It is located at RBP minus 10 hex, whereas our buffer is size 256 and it's below that, which means if we can overflow this buffer that we're reading into, we will be able to successfully overwrite this win variable. Okay, so let's see if we can do that. So if we since we're in the .0 version of this, we have all these pauses all over the place that will allow us to quickly confirm that we understand the race condition. So if I go into demo, and I get ready to edit this file, and let's see here. If we do this with world being the past in path, okay, and so we're on this first pause. So the first pause, let's see here. Okay, so we have a pause here. Right here is our pause. And it's telling us that it's about to call lstat on this file. And it's going to use that first lstat to check the size. So if we want to be less than 256. So we're currently less than 256. All we have in there is hello. So that should pass. So if we just press enter, in theory, it just passed those checks. We're on to another pause. And if we take a look at the next pause, which is right here, we can see that what we're about to do is we're about to open the path again. I guess we didn't previously open it, we just lstatted it. We're about to open that path, and then we're going to read in the data and do our thing. So we want to now overflow, basically. So we're currently paused, we passed the length check, we want to just put a ton of data into this file. So I just do 1,000 A's, and then we hit enter. We'll see our stack smashing detected, but more importantly, we'll see, hey, we got the flag because we overflowed the wind variable. Does that answer your question about level 3? Now, obviously, this is with the pausing version of the challenge, which allows us to make sure we understand the race. And then the next step will be kind of doing all of this fast enough, which we can get into, but see where the current questions are. Okay. So if we want to look into how we can do this sort of thing very quickly, let's see here. So Jan demonstrated this in his extended Q&A yesterday, but I can go, I guess, a little bit deeper into that in terms of making things fast, or at least recap it. So if I create some program here, x.py, and what I make this program do is, what do I want to do? If we open some file for writing, so let's say open that world file, we can open it for writing, and we write, let's say, we write a single A, and then we open this file again for writing, and we write 1,000 A's. Okay. So if we run this program, how do I want to do this? Trying to think what the easiest way will be to show this. We will try to use emacs for this, I guess. If we run this script and we look at world, we'll see that, of course, it has 1,000 bytes, right? The first thing it does is it writes a single A, and it's just one, and then 1,000. So if we quickly comment this out, oops, and we run this again, and then we look at it, right, it's 1 byte. Hopefully this makes sense, right? If we, on the other hand, run this rapidly, So for instance, how do I want to show this? We need another shell. Okay, so if I do lsal world done. All the issues, I'm in this crazy emacs shell. Let's do, I think this will work. Okay. If I do while true, do ls al world done. Okay, so this is very rapidly looking at the size of this file, and we can see that the current size is 1, which makes sense. Okay, if we run this program and we run it this way, we can see it switches to 1,000, and the next thing we want to do to test this is put this in a loop. So if we do another terminal, and we do while true do python x.py run. Okay. We can see that almost always in this bottom right terminal, it's 1,000, but occasionally it flickers. And when it's flickering, it is actually being 1. So this is maybe if you're just starting these challenges, not necessarily intuitive. So we've said that we want to kind of switch back and forth between being size of 1 byte and being a size of 1,000 bytes. And we're almost always being just a single byte. And maybe the simplest solution to that would be, okay, well, if we're only occasionally going to be 1 byte, then what if we just put this in a for loop so it's more often? So maybe we just do like for I in range 100, and then this is going to make it 100 times more likely. And we can see that that seems to be true, though I think it's flickering with zeros in there as well, probably when it's empty, but that's fine in our case because we just want it to be 1,000 or 0. I guess what we could do now is we could see, hey, does this do what we want to do? So we've got our script constantly running. We're flickering between these sizes. Maybe it'll just work for us. In fact, I don't even know. Maybe it actually will work. So if we run challenge baby heap level 3.0 and we pass it world. What? Challenge baby heap, or not baby heap, baby race. Very confused. Challenge baby race level 3.0 world. Okay. If we press enter, we press enter. In this case, it did not work. But what if we do the following? If we do while true, actually just to confirm what I'm about to do, if I do challenge baby race level 1 or level 3.0 and we redirect dev null as our standard in, so basically bypass these pauses, and we also pass. So there's a question, isn't it random if it works? Like I ran it 3 times and it worked once. Yes. Part of this, though, depending on the challenge, and some of these earlier levels, how efficient you kind of are won't matter, but in some of the later ones, it definitely will. The problem isn't just that, hey, is it going to occasionally work? Almost, I think all of them are just going to occasionally work. But it's about making it more likely to work. Okay, so if we do this and we pass it dev null as standard in, okay, there it failed. Okay, I wish I had, probably should learn how to actually split in tmux rather than have separate panes. That's the reason I'm using emacs as my window manager, because I actually know how to do it, but then the issue here is I don't know how to use these terminals easily. If I do, but we'll just roll with it for now. If I do while true, do challenge. Actually, you know what? I probably should switch to tmux because this is going to get annoying quick. Hold on. Let's do in this window here, let's launch up tmux and let's just Google tmux split. Which I think I saw. Control B. These. This is what I want. Okay. We will go with this route. Okay, so if I do Control B this, okay, awesome. And then Control B this, and I've got clicking on. All right, this is awesome. All right, let's do this route then instead. Okay, so if I switch back to here, okay, so this is our script that we were talking about where we've just decided to make this 100 times more likely. And then this, and then if we do while true, do challenge baby race level 3, or no. In this case, we're going to run our script. So do Python x.py. So there's a question in chat, tmux has clicking. It has clicking if you use this configuration file. So if you have a .tmux.conf in your home directory and you add the set-g mouse on, now you can just click between them, which is kind of nice. Okay, so if we do while true, do Python x.py, and then done, and then we do while true, do ls-al world, done, just to show this change. Okay, and then if we do the challenge, and we redirect dev null as a way of just getting past those pauses, because basically something's just going to always be input. And if we pass our world file, we can see we failed here, we failed here, failed, failing a lot. Here we failed in a different way though, file is too large. And but what we can do is we can put this in a while loop, just tons of while loops. And now we're going through and quickly switching this file, as we can see in the bottom right, and we're going through and running it. In this case, we don't have a very good way of seeing if we actually won, but what we can do is add a grep pwn, and we can see it does work occasionally, and probably occasionally enough that this is sufficient for us. But this is kind of insane of a way of doing it. This is probably just, in my mind, the most natural way that came to mind. Because if we saw, right, how often this is changing back when we didn't have this. So if we go back to this, we'll see that it's almost always 1,000, which means if we do this now, it's still possible to print out the flag. Okay, it still prints it out frequently enough in this case, because in this case, the race isn't too hard to succeed. But we can do better, is the ultimate truth. And the way that we can do better is that if we just put this in a while true loop, so here, as a way of showing this, if we do this while true do Python, if instead we do time Python x.py, we can see how long each of these executions is taking. So it's taking like 0.02 seconds to perform this swap twice. And that's very slow. So for instance, if instead we do for I in range 1,000, and we go back here, so it's taking longer, but it's not taking 1,000 times longer, is the thing to note, right? So before we had 0.02, and now we have 0.2, but we're doing 1,000 swap back and forths. So it's significantly we're taking 10 times as long, but we're doing 1,000 times the number of operations. And the reason we're able to do that is that by doing this operation 1,000 times in a row, instead, what we're doing is we're only paying the cost of starting up the Python process, which takes quite a bit of time. We only pay that cost once for every 1,000 swaps rather than once for every swap. Hopefully that makes sense. And in doing that, we're increasing. We can see now, for instance, right, that it's swapping back and forth between 1,000 and 0 much more often because we're paying that cost of sitting in the time where we're starting up the process much less often. So for instance, if I go back to this, right, and we go back here, we can see it's almost always 1,000. And the reason it's almost always 1,000 is because at the very end of the process, we set it to 1,000. And before it can go back to 1 or 0, depending on when it's wiping it, it has to go through the entire time of starting up this Python process. If there's any questions about that, please ask in the chat, because this is like getting through some of these later levels really requires understanding the timing of things and like narrowing windows. So for instance, like in level 5, you're going to have to do a series of operations back to back to back to back. It's not just going to be swapping between 2 states. You're going to have to potentially swap between like 3 or more states. And in order to successfully line everything up in a way where you're going to successfully do that, it requires really understanding this timing stuff. How long a syscall takes versus how long running this entire process takes versus etc. Are there any more questions in the chat about this? And of course, I showed for a while, I did 1,000 iterations, and I did that just so you could see the timing, but there's no reason you couldn't just do while true. And now, obviously, our timing information is going to vanish because this is going forever, but we're spinning our attempts much more often. And even this is a little bit slow. So for instance, since I'm not seeing any questions in chat, if instead of time, if we do strace here, we're going to see this. And this is kind of a mess to look at, so we'll just pause it real quick. We can see all of this lseek, write, close, open at, fstat, IO control, lseek, IO control. And we know that if we were going to write this, for instance, in assembly ourselves, we wouldn't call fstat or IO control. This is just taking up time that's preventing us from more easily being able to swap back and forth. So what we could do instead is in Python, we're kind of using this higher level thing that with this open. Instead, what we could do is use OS. So we could do import OS, and then we could do OS open. Maybe since we're in a while loop, let's just do this at the very start. If we do OS open world, and we do os.o write. Oh, I don't have, that doesn't look, that looks more correct. I think that's correct. We'll see if Python complains. If we open it here, and then we do os.write fd and then a here, and then we need a way to write 1,000 a's. We could add, I'm trying to think of the easiest way to do this. So one option would be to do an open write close in order to kind of get back to the start of the file. But instead we should be able to, could we just seek? Or that probably isn't true, is it? Because I think if we seek, we're not going to destroy our 1,000 A's. There's probably another syscall that would be able to wipe those out. I'm wondering if you actually have to just unlink the file. Simplest way, let's just Google. Hopefully someone's going to talk at a syscall level for us. Truncate. Is there like, there's not like a truncate syscall, is there? Everyone need to talk about bash ways to do it. Syscall. Empty contents of file with syscall Linux. There's gotta be a way to do it. I mean, it's possible the only way is just to unlink the file. Delete. Open file truncate. Syscall. The truncate 2. Well, this might actually be a syscall. Oops. Truncate. It is a syscall. Oh. Takes a path though instead of a file descriptor, which is a little sad. But we could do it. All right, that seems, I'm just trying to think, minimizing the number of syscalls, like having to call open, close, unlink, etc., etc., etc. There's a lot of syscalls, so we're just trying to minimize the number of syscalls here. So if we do os truncates world 0, oh, we might even be able to be super clever here. We might be able to write 1,000 A's and then truncate it to like 1A. Oh, that'd be cool. Let's see if that works. Well, I think this implies it's working. It's still going to 0. Do strace python x.py. Open. Am I not running this? Why am I not seeing like a truncate syscall? Oh, that's when it's reading in the source code. Oh, that's truncate. Hold on, does this just work? No, okay, it's crashing. This is why. This makes more sense. Okay, oh, it wants a byte string. Okay. We were doing strace in a while loop, and that's why it was continuously giving us syscalls, but we're crashing. It's a good idea to make sure that you're not crashing before you try and trace and see what's happening. Okay, now we're running. So why is this like going so crazy? Do we even have anything running? It's like still changing. What is this doing? Kill 320215. Someone's still changing our stuff. Here's Alex grep x.py. Kill 594646. What? Oh, you know what it is? I still have emacs with those terminals open. ANSI term. We need to kill these things. Just make sure all of these emacs shells that I opened are closed. Okay, that's all of them. All right, now we should see, okay, it's always the same size. That's good. That means we don't have a script running that's suddenly changing stuff. That is nice. Okay, if we run through though and run this again. Okay, now we can see it's changing between 1 and a huge size. I don't know why it's being a huge size. I mean, in this case, it doesn't really matter for us. What does truncate actually do? Man, truncate. We give it a path, give it a length. Says it's going to get rid of data. The file offset is not changed. It could be an issue because we still have this file descriptor. Oh wait, there was an F truncate, wasn't there? F truncate sounds like file descriptor truncate. Okay, there is. This sounds like it could be cooler. Okay, let's try that. Because I think file descriptors will be maintaining like an offset into a file, and that could get crazy. All right, let's try this again. Still large sizes. In our case, I don't think we really care. I'm not going to look too deep into it for this office hours, but I am still questioning what's going on here. But either way, we're very quickly switching back and forth. And if we strace this, strace this, and we pause real quick, we can see that we're just going back and forth between two syscalls. We're going between ftruncate and write. And in doing that, we're... I'm curious how often we're going between the two states. Ideally, we'd be going between the two states 50-50. So if I do... if I do for I in sequence 1,000, that'll do this 1,000 times. And if we cut out the fourth column, print 4, that is apparently not what we wanted to print. Let's try 5. Okay. And we sort this and get the counts of them. Oh, wait, we're not running. That makes sense. Why it's always the same value. Let's run it again. Okay, this time we're changing sizes. And let's see when we measure 1,000 times. Okay, so there's all sorts of sizes. But 775 times it was 1. Strange. Now, one reason for that could be that this truncate is slower. It could have something to do with the way that we're measuring with this ls-al. Actually, so we can quickly test this. If we strace with -tr, or in this case, we just care about -t, we run this, and we're just going to resize some stuff so we can more easily see it while we're looking here. We can see how long these things are taking. Okay, so truncate and write are taking about the same amount of time, it seems. So it could just have something to do with the fact that we're kind of racing ls to see what it thinks the size is and the way that we're doing that. Yeah, they seem to be about the same size. Okay, but there's another option here. So we're just, since no one's asking questions, I'm just going through how you can like start measuring time and like start thinking about it, of these things. Another option in this particular case is we could, in this case, we could create hard links. And this will actually be relatively similar to an idea that will actually be very useful in later levels. It won't be with hard links, it'll probably be with simlinks, but the same idea. Actually, I can do this with simlinks instead. So, and we'll see how I can do this with simlinks. So even though it tells us we're not allowed to use a symlink, so for instance, and yeah, we're just using level 3 as kind of the playground for looking at timing stuff. So if we run Python x, or if what do we want to do? If we run the challenge and we pass it /flag, we know that that fails because it contains flag. But on the other hand, if we do symlink /flag to flag, which means now we have this flag file in our current working directory, which points at flag. Of course, we can't cat it because it's just a symlink to /flag. And similarly, we can't pass this to the program. And again, I guess we'll make this larger because we're just focused on this one window. If we, well, I guess either way it contains the string flag. Let's remove this. If we do ln-s/flag to abc, obviously we can't cat abc. This points to /flag, and we can't pass this as our path to baby race level 3. If we hit enter, it fails because the file is a symlink. But the interesting thing to note is that this is just directly checking that particular file to see if that particular file, this ABC file, is a symlink. But what happens if we have this? If we have a directory, which is directory A, and we have a directory that's directory B, and we have a file inside of A called, let's see here, if we call this just file, and we go into B, and we have this be called file, and in this case, actually, if we do python-c print A times 1,000, that would print 1,000 A's, and we just put that into this file. Hopefully you can start seeing where I'm going. We have this A file, and we have this B file. And one of them is 0 bytes, one of them is 1,001. There's a new line character, whatever, that's fine. But what we can do now is we can do ln-s c to A. And what we have now is, wait, did I just do this wrong? I think I did this wrong. I think I had those backwards. Yeah, we have this file C in here now. We don't want that. RMC. What we wanted to do was ln-s AC. I got the order swapped around. And what we have now is we have this directory A, which contains file, which is 0 bytes. We have directory B, which contains file, which is 1,000 bytes. And now technically we have directory C, which contains file, which is 0 bytes. And the reason we have that is that C is pointing at A, and A contains something called file. And the really important detail here is file c/file is not a symlink. C is a symlink, but c/file is not a symlink. C ends up resolving itself to A, and then that contains a file which is not a symlink. So when we do this lstat on c/file, it is going to report that this is not a symlink. So we can see that if we do challenge baby race, and then we pass it c/file, it is not going to complain about that being a symlink. It doesn't say that this is a symlink, this is an issue. And the reason that this is cool is it lets us set up entire kind of situations of a file's state within directories, and we can just swap between those states by swapping this symlink. So now what we can do is we can do the following. We can do OS, and this is going to be a little bit slower, even though it's arguable because this behavior wasn't actually the behavior we wanted. For some reason, we were writing hundreds of thousands of bytes. But what we can do is we can do os.unlink C, which is going to just basically remove C. And then we can do os.symlink, and if I get the order correct, I swear I always mess up this order. I think this was what I did before, and it was correct, and I think it follows the same order in Python. AC, okay, yeah. And then we can do unlink C again, and we can do symlink BC. And now what we're going to have is we're going to, and maybe what we can do actually just to be safe is, how do I want to do this? I'm trying to think about if we start this script with a state where C doesn't exist, that would be an issue for us. What we can do is we can move this to the end so that we're always symmetrically doing that. That means this could fail in theory if C already exists. But what we can do is we can try at the very start, os unlink C. And then I don't know what exception it is. We'll just accept for all exceptions and call that good. Okay. And now if we run this, and we'll get ready. This just got crazy. Okay, so if we run this script, again, it's just going to be all the same. If we run this now, though, and we don't want to ls-al world, we want to ls-al c/file. Okay, that makes sense. A bunch of them don't exist. But that's interesting, though, to note that there's now this in-between state where this doesn't exist because we have been unlinking it, right? This exists. But when it does exist, we're correctly in one of these two states. So if we, as a way of measuring this, get rid of standard error. Okay, so we can see of 1,000 attempts, 134 of them ended up with size 0, 129 of them end up with 1,001. So this is pretty good from the perspective of balancing it. It's no longer very good, though, from the perspective of, I mean, this means 80% of the time the file just doesn't even exist. And we probably can see that if we do, if, for instance, we run this and we pass C file and we redirect dev null to make it so those pauses don't happen. So we're going to see a lot of these error failed to get file status. That's going to correspond with when ls-al isn't giving us the path. So, I mean, it's not always going to give it, but according to this measurement, and maybe you say that this ls measurement isn't the most accurate way of measuring it because ls has its own performance characteristics in terms of at what frequency it's checking this file. That's not going to be completely identical to the challenges characteristics of checking the file, but it's probably close enough. Either way, what we're saying is that, hey, 80% of the time this file doesn't exist. That's not very good for our race. Failed to get the status. We did see the size, though, but we're running this a bunch. Okay, what we can do is we can do for I in sequence 1,000, do this, and we can grep for an error. Would that be the way to do it? I think. Grep error, we'll do that for now. And sort that unique dash c that. Okay. So actually, when we're getting these stack smashing detected, those are technically successes. That's when we would have gotten the flag. Hopefully that makes sense, because that means we overread, which means we overflowed the win variable, which means it would have printed it out to us. So we can consider these all successes, which is kind of nice because it's on standard error. But then it's failing as we said, so we just did it 1,000 times. So similar to LS failing about 80% of the time, this is failing about 80% of the time. And then 120 of the times it would be kind of in this state where it is 1,000 bytes, but it's 1,000 bytes at the wrong time. And then this like 2, 3, 4, 5, 6, 7, 8 times, we'll say approximately 10. And it makes sense that it's approximately 10. And the reason it makes sense that it's approximately 10 is because what we need to have happen is that we need this thing, which is like 10% of the time, and this thing, which is about 10% of the time, to line up in the correct order back to back, which puts us at about 1%, right? And then this is why this is about 1% of the time. So this all hopefully makes sense how all of these performance characteristics are aligning themselves to reflect in this data of us measuring everything. And everything is also just approximate, right? Could be weird characteristics going on. And potentially one thing we'd want to do is increase our odds of success. So obviously if we win 10 times out of 1,000, it's good enough for the challenge. But in future challenges where you have to start optimizing, really thinking about this stuff to make your odds more likely helps a lot. What could we do? So the most obvious thing to me that's standing out is that we're spending an insane amount of time where it's failing to get a file status. It would be really nice if we could get this down to 0 cases. Yeah, so maybe we can see, I mean, what this means is that 80% of the time we're in like this unlink and the symlink hasn't quite finished from the kernel's perspective yet. What could we do? So one option, and this is probably a pretty good option, is that we could parallelize some things going on. So if we do if os fork, and then else, so this is going to now, we can kind of think of it as we have two processes now, right? We have the one where this is 0 and non-zero, basically. And what we could do here is we could do while true os.unlinkc. Okay. And then in this one, for instance, and we can see what the results of doing this will be. Why do these indentations look different? Okay, that looks better. I'm confused. Is this? I don't know what's going on there. Okay, while true. And then we could say let's just start by seeing what this looks like for the performance characteristics. AC and BC. So this should be approximately, I mean, it's going to functionally do the same sort of thing. It's just going to do it at a different rate. We're just going to have one thread or one process constantly unlinking and one process constantly trying to symlink A, symlink B. And there's going to be an issue here for all of this. Now that this is all happening like kind of simultaneously, is that all of this stuff could just fail at any point. Because if we try and unlink it and it's already unlinked, this is just going to throw an exception in Python. So we just catch those exceptions. And accept, pass, try, accepts, pass. Good enough. Okay. let's see what this looks like now. So if we run this again, so we're running it, let's see from our measurement using ls what that looks like. Okay, this is looking like it's basically the same. Interesting. And if we run it from here, I mean, it happened to be less here. Maybe we should have done more trial runs. Seems like we brought it down. I think it was about 800 before. Well, what we can do now that we have this split out is we can do this. We can just have more processes simultaneously doing this stuff. So what we can do, for instance, the first thing we could do is we could add in another fork. And we could do these in separate processes. And we'll say else here. And we'll say while true. Okay, and now what we've done is now we have 3 processes. And in one process, we have this constant unlinking, and another process, we have this constant simlinking to make it be A, and in this process, we have it constantly trying to make it B. Let's see what that looks like for increasing our odds of success. It brought it up a bit, we can see. Now we're in like the 160s. And if we run this, we should see, doesn't seem like it actually, well, maybe it did. We're getting more. It's hard to say, right? We'd have to run tons of tests to really know what we're doing here. See, it did only succeeded a few times. But now that we have it situated like this, we can do really simple Python multiprocessing by literally just doing os.fork, 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 os.fork. And what this is going to do is that every single time you call os.fork, you're splitting the process in 2, which means we just split this process into 16 processes. And then we're going to split those in half to do these. So now we have a ton of processes doing these simlinking and only one process doing this unlinking. So we're going to be spending a ton of time attempting to do simlinking. So now if we measure it, assuming I'm not completely crazy, hopefully we're going to see that we have way more successes now. We have way more time spent where it's an existing file. And let's see if that's true. Okay, it definitely jumped up. Let's see this. We definitely have way less time being spent where this is the case. Interestingly, though, we only succeeded 3 times, and that's kind of weird. But either way, we can definitely tell that by doing this, I don't know why we're succeeding less times, though. We've definitely accomplished our goal of getting this failed to get file status way down. But why are we not winning more as a result of doing that? That is weird. I mean, just to completely verify, I think whenever we see that stack smashing detected, we should have won, but let's just grep for pwn.college to be safe. If that's true. Well, this time we only got it once. I wonder if because of all of these Python processes, like we're maxing out our container's ability. Our container only has the ability to run 4 vCPUs. We're definitely maxing that out. So for instance, you can see that all of these Python processes are taking 11.5% of the CPU. And in total, this is going to probably add up to 400%. If I get rid of this and just add in another os.fork, we're probably going to see this cut in half and have twice as many. PS aux. Yeah, this cut in half now. So we're kind of at our limit. Like we're doing things as fast as we possibly can, but we only have 4 CPUs within the container, and the reason you only have 4 CPUs within the container is because this is the sort of code you might be writing, and if someone starts writing code that looks like this and uses all of our 40 cores or whatever, 48 cores, I think, it would be very sad for other people. So we may just be, maybe we want to bring this down to 2 or something. Okay. So run this. But interestingly, I don't know, its performance characteristics get really weird. Like you really have to just try some level. You're trying different things and measuring it. I mean, obviously, as soon as you have the flag, you have the flag, but let's try some things. Okay, so if we do scared of standard error, let's just actually measure this. How many times we win, which is ultimately the thing we care about. Let's do it 10,000 times. Grep for pwn.college. Obviously, at the point that you're measuring how often you succeed, you've already got the flag. There's a question that how did you resize the window with mouse and tmux? I can only use Control-BZ to focus on one window. So yeah, I can use the mouse to drag this around, and the reason I can do that is because of my tmux configuration, this set-g mouse on. So you need a .tmux.conf file with that, and now you can use the mouse to do all sorts of things. So for instance, you can also just start scrolling, right? Which normal tmux you can't scroll, it goes all crazy. So I'd highly recommend adding this configuration option. Makes tmux just easier. I mean, obviously you can be more efficient using just the keyboard, but I don't know. It's nice to be able to click around. Okay, so we succeeded 50 times under this. Let's just run it one more time. I mean, we're running at 10,000. It should be the same-ish. We succeeded 5% of the time before. Oh, and this just suddenly doubled. This is what I'm talking about. Stuff goes crazy. We didn't change anything. Why did we just get twice as many victories? It's a crazy world out there. At some level, you're just kind of depending on luck. I mean, you can do things to influence your luck. So I would definitely wouldn't say that, hey, I'm running my solution for 10 minutes. It didn't give me the flag. I'm just unlucky. No, it's probably going to be the case that if you run your solution for 10 minutes and you don't get the flag, you probably just don't have very good odds. I mean, in theory, you might even have the odds to win it, even if it takes 10 minutes. But I'm pretty sure we've designed these challenges in a way where none of your solutions should take 10 minutes to run. Yeah, it's so even doing 10,000 attempts, it's just crazy. I don't even know how to measure this if it's going to go between 50 and 100 with like adding more forks. Whatever, we'll see what happens. We'll just go real crazy, add a bunch of forks, really max out our CPU that we're allocated here. Yeah, if we like look at this, these are all using like less than 1%. They're really competing with each other to run. And then if we run this, so we had somewhere between 50 and 100. Let's see how many we get of this. Actually, you know what? We should probably just do 1,000. Because I think with us pegging with all these cores, even just running this is going to get slow. Maybe, well, oh, it just completely failed. See? Throwing more processes at it isn't necessarily a good thing. We brought it all the way down to 0 with all these forks. Not good. Curious how many times we have these files. See, we're improving our odds of it missing, right? Of the file not existing. In this case, like, it barely ever is missing. But apparently the file not ever missing isn't necessarily a good thing for getting the flag, as we can see here. So yeah, even though that file is always existing, it's not great. I'm kind of curious what the order is. Like, is it always going back and forth? Sort unique. Let's not sort it. Let's just quickly, a bunch of zeros. Oh, this is crazy. And then it's going to be a bunch of thousands. See, those are like not the sorts of characteristics you want. So even though we made it so it's, that is very strange. Even though we made it so it's like a 50-50 split, we have like these long runs where it's like a bunch of 1000s, then a bunch of zeros. And that is definitely not how we're going to win this race, which makes sense why we're, in this case, we ran it 1000 times, we got 0. Like, this is like the dream of what we could set up the code to do. And I'm not even entirely sure how you do this. You would make it so literally every single time you check that file, it just constantly was flipping back and forth. If it was 0, 1000, 0, 1000, 0, 1000, every time you check, it just alternated. Because then we would always win the race. But assuming that we were in sync. If you were literally that perfect, you'd have to be correctly in sync, but same idea. This is not good, because if we check in here, and this is why we're failing, right? We're going to be 1000 in a row and then 1000 in a row, and it's just going to fail. We need it to be, we're looking for this, like it needs to be 0 and then 1000 when it checks. And we have those occurring, so I'm kind of surprised it was 0. But that is the frequency we need. It needs to be 0, 1000. All this optimization is going to be relevant for meeting other conditions and other levels, I imagine, right? So the big optimization that I was trying to showcase here that is kind of overkill for this level, but is going to be incredibly useful in, like, you'll see in like in levels 5 and 6, I think, is this structure of unlinking and linking, because that is a very quick way to get your file state to change. You don't have to create the file and then write to it and then close it and then like those 3 syscalls and then do that again but in some other way, and like all these syscalls right now. So the way I'm thinking about this here is if we strace challenge baby race level 3 C file, and we want to just pass it dev null. What we need to happen is when this lstat, where is this? I see. Oh, there's also these writes. These writes aren't going to exist in the .1 version. Okay, what I'm trying to say is that when this lstat happens, we need that file to be in a very specific state. And then in the case of the .1 version where we don't have this pause stuff, so we kind of get rid of these 2 syscalls. Actually, in fact, as I'm talking about this, let me show the timings. We're going to do this lstat, not this lstat. Why would there be multiple stats? Oh, we failed this time, that's why. Okay. File too large. File too large. File too large. Okay, good enough. So what we need to have happen is that in this lstat, we need our file to be in a very specific state. And then in the .1 version where these writes don't happen, immediately in the next syscall, we need that file to be in a different state. So we kind of have this one syscall room to switch between these two states. So if on your attacking end, you need to perform a bunch of syscalls, and you need to somehow squeeze a bunch of syscalls in between this lstat and this open, your attack is like never going to succeed. So the dream is, as part of this attack, is that you want to minimize how much stuff you need to do between this syscall and this syscall, because this is the gap that you're shooting between. And a very good way of doing that is setting up whatever the structure you need of your files and simlinking to get between the two states. We saw that throwing a bunch of forks at this is no good, but if we get rid of all those forks and just have 3 processes, in fact, let's just see how often that succeeds. Okay, Python's gonna go crazy. Pico Python. Okay. For I this Python x.py this. Right, when we're that failed also. Why is that failing? Really? I'm slightly confused on exactly what the right number of os.forks are there. Okay, apparently 8's too many, 0's not enough. 2 is pretty good. You know, maybe 3 is even better, who knows, but moral of the story, hopefully it's clear that the reason that we're doing these optimizations is that we have a very small window. We have that lstat followed by that open, and we need to change the entire contents of that file in between. And in later levels, the number of steps that you would have to do, it's more steps. It won't be just changing the contents of the file. It might be changing some directory hierarchy, for instance. And a quick way to do that is using simlinks. Okay, are there any final questions? Hopefully I can just have another office hours once people have had some more time to work on these challenges and kind of more directly address specific questions. In this office hours, I've just tried to demonstrate how you can start timing stuff and at least somewhat kind of wrapping your head around these windows that you have access to. In a lot of cases, it is just kind of messing around with your solution and trying kind of slightly different configurations of it, or just let it run for 2 minutes, etc. But these are some of the ways you can start thinking about it. It definitely does help to start optimizing. Clearly, though, we've seen that just throwing more forks or more processes at it is not strictly the solution to your problem. Though, depending on how you have it set up, throwing more processes at it could actually, just depending on the performance characteristics, work. So for hints on level 5, I don't know if specifically if you're referring to 5.0 or 5.1. So, I mean, obviously the first thing to do is in these levels solve the .0 variation to make sure you really understand what constraints need to be changed in between the different window timings, which is much easier if you have the program literally pause itself at those timings. In terms of the .1 version of trying to go through and speed it up, I think using simlinks is going to be very helpful, setting up directories. So the key insight here that I'm saying is going to be very useful in 5 and 6. At least I've seen a lot of people succeed by using this sort of strategy, is this idea that even though, what happened to C? oh, we're kind of going crazy, right? Even though c/file in this case, let's stop this so I can say this final bit. LNSAC. Okay. So even though we have this c/file, and that is going through this C directory, which is a symlink, c/file is not a symlink. C is a symlink, c/file is not a symlink. It goes through a symlink, but the very final path, or the very, I don't know, like the base name or whatever, the very end node itself, which is what LStat might be checking, that very last node is not a symlink. It just happens to have a path that goes through a symlink, but this is not a symlink. That is a very important detail that should help a lot with levels 5 and 6 in terms of being able to make things fast. Okay, I'm going to end my office hours. Hopefully I'll have time to do another office hours when people have had more of a chance of working on the levels. And I think Jan said maybe he would do an office hours. So depending on that, maybe I'll do another office hours on Friday or Monday. I think Monday probably is the best, but we'll see. I don't know. And then in the meantime, feel free to ask questions as always in the Discord. All right. Thank you everyone for coming to my office hours. See ya.